Okay. All right. Welcome to the John Postel Distinguished Lecture. John Postel, I'm sure you know, was used to hang out in that other building called Bolter. Have you been there? Right.
Not sure. I remember
Yeah.
having lunch with John, but I can't remember what.
Yeah. So, and Len Kleinrock told me the story of how he was working for somebody else, but then Len got a grant, and so then they just decided to all work together and went. And so it was an exciting story. Wint has come here before. I'm just so excited to have Vern, who I've known for many years. So first of all, how many of you have read the book 1984 by George Orwell? Wow, that's a lot of people. Okay, how many of you have heard of the character Big Brother? Very good. Okay, you probably didn't know this, right? And George Orwell didn't know this also, but Vern invented Big Brother, right? And in fact, Vern was so annoyed that George Orwell didn't give him credit that he decided to build a system called Bro, right? That actually snoops on all of you, and if you check, probably it has information about your social security numbers.
Wait a minute.
So, no, but Bro is actually a really cool intrusion detection system, one of the first of its kind, open source, which is great for actually handling bad guys, right? Vern has always been on the side of the angels, right? I would say. Hopefully in this company too,
Sure.
right? I'm
Oh, yeah.
hoping. Yeah. So you haven't been switched to the dark side
Nope.
yet? Okay, got it. And so Bro has been this very influential system, and Vern has actually made a series of really influential papers. And in intrusion detection, he and Handley wrote this paper on something called normalization, which I think is a really seminal paper. But actually, he's famous also for measurement. So the internet sort of succeeded and it became popular, but as it started growing, it started having these second generation problems, right? Just like, people get diabetes and this thing as they get after they make their basic needs. So security and measurement sort of became big time things, and Vern has been kind of an unquestioned leader in both fields. So very early during his PhD thesis, he asked the question, what's going on in the internet, right? How do I know how traffic works in the internet? And everybody said, how do you do this? Because, you're one person in Berkeley. But an amazing social and technical experiment, he was able to convince a bunch of people. I think you even asked us at wherever, UCSD?
Worcester, yeah.
And Worcester, who knows where. And so to get a machine, and he got all those machines and he triangulated, and there was some astonishing results, like I think asymmetry, right? That was one of those things that half the packets you send come back in a different path. And that was astonishing to a lot of people. It broke a lot of assumptions and lots of things like that he found out. And so measurement and security and intrusion detection, and he's won lots and lots of awards. The ACM SIGCOMM Award, he's won the Grace Hopper Award, is that right, too? Yeah, and which is also, I think, for building influential systems, right? Not just talking about it, right? So here he is to tell you about some of his recent work. He's also been doing a lot of recent work with Stefan Savage at UCSD and a bunch of people on the economics of crime. So it's like the famous adage, look for the money. They've been sort of figuring out sort of where the money goes and trying to sort of break security problems at a more fundamental level. So I have no particular idea what he's going to talk about in this talk, but it'll be good.
Thank you. Is the sound working okay? Great. Well, thanks for the introduction, George, and I'm really pleased to be here. The asterisk up there by my name is because I'm going to talk about work done with a bunch of colleagues and students and the like, and don't really have room to list them, but I want to convey that up front. So what I want to focus on is detection. I've always found it interesting. I've worked for decades on detecting misbehavior, miscreants, bad things, and worked on a number of detection problems. Some of these detection problems are you're going after something kind of explicit, like, oh, if I ever see this URL or this pattern in a packet, it's bad. Now I'm going to focus today on stealthy attacks, where the attacker really doesn't want to be detected. And these I find fascinating because they represent a major pain point for pretty much any enterprise is worried about stealthy attackers, the ones that they don't know and don't identify. And the attacker gets in unidentified that can do enormous damage. Took a long amount of time to find them, clean them up. And these are rare events. It may not happen more than a few times a year for a given enterprise, and yet they can be more costly than all of the routine infections and ransomware and whatever else. So, hard problem, and a problem that I think is apt to think about today as, in some ways, a big data problem. But and that's going to be one of the themes. So let me talk about this in general terms, and then I'm going to go into some specific examples of detection. So we are looking for what in the title I referred to as noodles. We're looking for just a little trace of activity that is buried inside this enormous amount of non-malicious activity. So the art here is, how do you find that thing? And particularly, it doesn't want to be found. And there's going to be some themes about this. One of them is the one I just made, which is, think about this as a big data problem. We have data at scale problems. And with that is going to come with real-world data, which all of these, when I talk about, are based on real-world data. Immense diversity in the benign stuff. More than easy to appreciate if you haven't worked with data at scale. It's messy. And that makes lots of natural approaches that work fine on small data sets will fail. They will fail because there are rare but benign things. And so any sort of detection model based on, I'm going to find the rare weirdos, is going to find those, and yet they're not problems. So in particular, sort of hovering over all of this, anytime we talk about big data analysis, is machine learning. Can we use machine learning to do these detections? And I'm going to frame, this is actually going to be really hard. These are not amenable to machine learning very well. And the problem is this diversity and base rate issues, meaning the thing we're looking for is incredibly rare. So even if we have very low false positive rates, just due to the immense scale, we're still going to have most of our detections be false positives. I'll illustrate that in a bit. So the strategy, and this is going to be manifest in each of the three detectors we look at, is going to fundamentally have to leverage the semantic structure of the specific problem. So we would love to be able to just take a bunch of generic tools like machine learning, apply them, get detectors. It's not going to work, unfortunately. So we're going to have to leverage the nature of the specific problem we're going after. And we're going to have a strategy which is, step one, come up with filters that can hugely reduce that ocean of activity down to something a lot smaller. And of course, we don't want to lose the good stuff when we do that. And then we're going to go after not the entire problem, but a subset of the problem. And we're going to try to detect it, and we're not going to try to get it perfectly. We're going to try to give high-quality information to a human. And the human is then going to look and determine, is this really a problem? That's going to be the overarching sort of pattern for these detectors. So we want to, we're going to have to settle for give the analysts a tractable load. We're not going to be able to just automatically find these problems. All right, that's the overall framing. So what are the three problems? We're going to look at finding covert tunneling, and I'll define that in just a minute. That's one detection problem. The second is we're going to look for detecting attackers who spread their activity out so that point-wise, none of their activity looks strange. And finally, we're going to look at detecting a form of social engineering, where the attacker is manipulating people. So let's start with covert tunneling. The setting for this is that an attacker has already compromised an internal system, and they're inside an enterprise that is pretty well locked down. So the attacker wants to get communication between that system and the outside world, so a system he controls in the outside world. And they either want to enable ongoing access via this communication channel, or they want to exfiltrate information they're stealing from the enterprise over it. they're going to bury the communication inside some seemingly benign, surely it's harmless network activity. That's them trying to avoid being detected. And there's several ways to do this, but one that's really attractive is DNS, domain name service lookups. Why? Because DNS is ubiquitous. Computer systems always have to do it. Even if their web traffic is controlled, they'll still generally be able to issue DNS lookups. Now, they can't do it directly. They do it indirectly. So here's an example of the two models. The system on the left has been compromised previously. And we're not going after that initial compromise. We're going after the subsequent use of it. The firewall there is preventing it from doing any regular communication to the outside world, like nothing. They can't talk at all. However, they can issue DNS requests to look up names. And they don't issue the request through the firewall. They issue it to a local server, which is then, if it has it in its cache, will answer directly, and if not, will make the lookup on their behalf. So the lookups will go out, and they can go out to a server under the attacker's control. They don't even come from the client directly. They come directly from the DNS server at the site. That's going to be the channel the attackers use. This is not hypothetical. No, this is an actual vector used to exfiltrate information and for control of subverted systems. All right, how are we going to detect that that is going on? And I'm going to walk through sort of some initial thinking about it and then sketch how this problem's pretty darn hard and then circle back and still make a good stab at it. So you might think, well, they're embedding information in these queries that are then going to be relayed to the outside system, and the embedding is going to make it look funny. Not going to look like, human chosen names. It's going to, because they have to embed data that they want to communicate. And so we should look for that. This is not going to work because the attacker has enormous leeway in how they might encode the information they want to exfiltrate. They don't have to, just have it literally sitting there as byte patterns. They can use any sort of rewriting of letters and characters. So that detector is problematic. Then we might think, okay, but they're going to make these big lookups because they're shipping lots of data. And we'll just look for big lookups. Surely they're not that common. And also, the communication is going to be conveying lots of different data because the attacker wants to move, say, a big document out. And so there'll be all sorts of different lookups going to that remote server. We'll look at lots of different lookups being sent. So these might be ways you think when you're confronted with this detection problem of, all right, we're going to go after one of these angles. And they're not bad ideas per se. Now, this is where the problem gets very interesting research-wise, which is that if we have data that we locally generate to think about it, say we go to our department's DNS server and look at all the lookups on it or something, we don't have data at scale. And we might look at it, and it is tame enough, so to speak, in terms of big lookups or lots of different lookups, that we come up with an algorithm that could do the detection. It's often underappreciated that if we work on small data sets on these detection problems, they are not going to generalize. And this is a huge pitfall because you could put a lot of work into that data set and do quite well on it, and you still don't have a useful thing at the end of it. The issue is the results don't scale up, and they don't because real-world use at scale is just weirder than you would think. It's more wild. And that's I don't have a crisp way of putting that, but I think I have an attempt here. No, it's on a later one. It's just more surprising than you expect. Even after you've worked for a long time with such data, you still get surprised at how weird it can be. I'll show you some examples in a minute. So we're going to need data at scale, and we're going to need lots of it. Because remember, we would like real needles in haystacks. So not only do we have data at scale, but there might be 1 needle or 2 needles a year. So we're going to need a lot of data. This is hard. This makes the research difficult. Finally, we're going to need a context where we know we can figure out, did we get it right? So we need some way of obtaining ground truth. It's also hard. All right, so for this problem, we went after data. This was done with my research group working with folks at IBM. And we got data from IBM Research, that's the top row, Lawrence Berkeley National Lab, NERSC, which is a supercomputer center, UC Berkeley, China, which is an aggregated site in China from a number of universities there, and SIE, which is this massive passive DNS data source gathered from, they don't tell you who, but clearly some ISPs in the US and the like. And you can see in time span there, we have, for some of them, years of data. And a total 230 billion lookups. So that's the haystack. Now we want to look inside the 230 billion lookups to find exfiltration or surreptitious communication. And we don't even know it's there. That was the iffiest thing about doing this research, is we didn't even know if we could find something in it. We're just hoping somewhere in there there's some misbehavior. All right, now let me return to this question. Can we detect it? We'll look for these really big lookups, or we'll look for, there's a whole lot of different lookups to the same server. You know, these are ways to detect that somebody is communicating a lot of information over the channel. And this is where we get, it almost seems like emergent behavior, which is we have data at scale, and it just has really strange stuff in it, and they're benign. So here's a plot, and it's a little hard to track, so let me sketch it. So we're looking at how big are the domain names in lookups, because this is going after, is it really unusual to see a big name in a lookup? And so is it, and I start at 50 bytes, 100, 150, 200 bytes. So those are really big names. And then we've got the count of how often we saw that many or more log scale. So the plot here comes from a single day. And the single day at Lawrence Berkeley National Lab had 58,000 different lookups that were 100 bytes or more in size. If you're thinking about DNS names, you think about www.facebook.com. I mean, how do you get a 100-byte lookup? Much less, how do you get 58,000 different ones in a single day? Here's some examples. So that top one, Sophos, is an antivirus system. And it appears to be that all the installations of Sophos will compute some sort of encoding of who knows what, hashes of binaries or something, and ship it out to Sophos' server to say, is this bad? The second one, Spotify, I have no idea what they're doing. So they are somehow communicating information off the user system. The third one is a license manager for crashplan.com. The fourth one is, if you're a networking person, is actually pretty amusing. And is clearly somebody who is frustrated at some configuration issue. And then the fifth one is just junk leaking out of somebody's system that should never have been looked up in the first place. It's not a legitimate lookup. So it would have been legitimate had it stopped, had it been, I think this is .local. It's supposed to be local, but they had a search path of johnsonhouse4.members.mac.com. And so because of the search path, it went out over the wire. These are not attacks. Sorry, yes, these are not attacks. And so, and I could fish up 58,000 more of these from that day. And now you begin to appreciate this problem as a mess. And you might not have seen any of that if you looked at a small data set. It's just not going to be there because they're rare. Okay, now, how are we going to detect the bad ones of those? We know we have tons of them that are benign. And here we go to this theme of we're not going to perfectly solve this problem. We're going to solve a subset of it. So we observe, this is an intractable problem if the goal is a bad guy can never communicate any information over DNS to the outside world. Because, for example, they could convey a single bit by whether they look up 0.foo.com or 1.foo.com. And they might just issue one lookup, and there's no way, unless we have external knowledge about how the attacker is working, that we could look at that one lookup and know that it was bad. So that's a thought experiment saying we cannot solve this problem perfectly. So here's the idea. We're going to estimate for each client inside the enterprise what's a bound on how much information it possibly sent to a given remote DNS server via its lookups. Let's construct a bound. And then we're going to, so this is how we're boxing. We're going to construct that, and then we're going to say, and then we're going to be unhappy if the bound is above some threshold. So we're not going to try to do 1 bit. I just illustrated that's really hard. But we might pick a threshold, say 4 kilobytes a day. We're going to be unhappy if a client is able to exfiltrate 4 kilobytes a day to some remote server, and it's a bad guy. So we're going to pick some bound. Below it, we're going to give up. And above it, we would like high-quality instances to give to our analysts. So we know from our data that many, many domains have more volume than 4 kilobytes sent to them. So we're going to have to filter them down. That's our first problem. And our second is we don't know how the attacker is going to encode. They might encode all sorts of different schemes. And they could even encode just in the timing of their requests. They could look up the same name over and over, and the number of milliseconds between lookups is the ASCII code of the next byte. Who knows? So ideally, we deal with all of that. Okay, how can we do that? Here's the key idea. We're going to construct a sound, conservative bound on how much information a given client communicated to a given server in a day, say. And we're going to use lossless compression to construct it. So we're going to take all the queries from the client to each place that it queried from. We're going to represent them in terms of their name. Hey, I looked up foobar.xyz.com, so foobar would be the thing they looked up. The type, I looked up an IPv4 address, an IPv6 address, a PTR, whatever, and the timing. And we're going to represent these in a form that is designed to be compressible, but compressible with lossless compression. And then, so we're going to have this whole series of lookups, and then we're going to throw these generic lossless compressors at them, like gzip. And we can throw a bunch of compressors at them and just pick whichever one compresses it the smallest. That's a bound on the amount of information. It's an upper bound. Do it? Yeah. Well, if you have to do a lot of lookups. Yeah. And they're random. Yeah. All right. Now, and this is sort of how we are taking this problem, this needle and haystack problem, and we're going to break it down with a whole bunch of filtering, a filter cascade. This is my last slide on sort of the technical part, because I want to get to these other detectors as well. Let me walk you through this. We're taking 1 day of lookups at one of the sites, Lawrence Berkeley Lab. 45 million lookups that day, going to 65,000 targets. A whole bunch of them, we can reason about, that lookup actually wouldn't go outside the site. It would hit the cache. So throw them away. a whole bunch of them we can look at and say, that is a boring lookup. It's either for a domain that doesn't exist, or it's for the site itself, or it's for example, the site's external partner. So if the site's external partner's name server is compromised by the bad guy, we're in a world of hurt. And this sort of exfiltration is peanuts compared to the problems we have. So we throw out a bunch of uninteresting ones. Now, you may remember I was saying we're going to construct all these time series of lookups, and then we're going to gzip them and the like. That's slow. So we have a fast estimator that gives a upper bound on the size that's not as good as gzipping, but it's a start, and anything that it says is below our threshold, we throw out. Because we know once we gzip it, it's going to be smaller, if that size or smaller. Then we do the expensive compression, and we throw out all the ones that are below our threshold, and we use 4 kilobytes a day. And then at the end of this, we get a whole bunch of targets, domains, to consider. The first day we run this, we get dozens of these. Facebook.com, Google.com, Akamai.com. And we have to look at them and assess them. Some of them we just make fake sharing arguments. You know, if Google.com is compromised, we're so screwed that I don't care about this tunneling. So fake sharing says that's not how the attacker is getting out. Once we've looked at it, we're not going to look at it in the future. So the first couple of days, we have to look at a bunch, and then subsequent days, we're looking at these domains, and a bunch of them are ones we already looked at in the past and made a decision. So we're not going to bother looking again. And on this particular day, one suffix survived. And that's the one that the analyst then has to go look at. All right, so we have not made a solid detection, but we've given the analyst a high-quality reason to look at that thing. So we looked at 230 billion lookups, and we found 59 tunnels. That was pretty cool. Some of these we could externally figure out we should be able to find because there's tunneling toolkits for DNS, and we could look for those using signatures. And some of them were surprises to us. None of them appeared to be actual malicious things. They appeared to mostly be people like, for example, one of the ones at Lawrence Berkeley Lab was a tunnel over DNS set up by a staff member to get free internet access at airports. So you get to the airport, and you can do DNS lookups before you pay the money. And so they would just do DNS lookups on and on and on, and they ran the tunnel. So that one actually was coming inbound. No, actually, it was still on their laptop when they came in. Here's the bottom line. 1 to 2 of those things that survived the filtering per week at the enterprises. So for the cost of an analyst looking once or twice a week, we can now find any exfiltration that's 4 kilobytes or more to a remote site. All right, so that's one example of starting with this immense ocean. There were needles in it, and we find them. There was not a success story in this batch, but this was all old data and some of which, but hold that thought because we will have some success stories. Okay, that's one example. I'm going to walk through 2 others to give you a feel of sort of how this thinking generalizes and how it can be specific. And now we're going to talk about stealthy distributed attacks. Let me begin with talking about a common threat enterprises face, which is SSH Bruteforcing. So if an enterprise allows password access to its local servers via SSH, then they have a headache, which is there's incessant activity out there that's trying to guess those passwords all the time. So I guarantee you right now, UCLA has somebody trying to brute force SSH passwords coming in. Because surely this campus allows password access. It's too big and disparate to require public key only. And once you allow it, you have this problem. So the attacker is going to try username password pairs over and over and over and try to get lucky. If they get lucky, it sucks because now they've got an encrypted channel into your site. And so you can't read what's going on in the activity. So it's going to take the attackers typically thousands or tens of thousands, hundreds of thousands of attempts because they don't know the passwords. I mean, they've got lists of things to try, and they will try those. And if a single remote machine launches this attack, it's really easy to find them because they make thousands of login attempts. They just stick out like a sore thumb. Easy problem. Easy problem to solve. And that's an instance of a threshold-based detector. So there's some detector that says, you know, if you make 50 or more failed attempts, to heck with you. You're a bad guy trying to brute force. In fact, we were able to show in this research as a side note that I'm not going to be able to get to that 20 is a very sound number to use for that. People do not screw up their password 20 times in a row. They give up before that. Now, consider the attacker who doesn't use one machine. They use thousands. Each machine is just going to try a few times. That is distributed stealthy attack. And we would like to be able to detect that. And the problem we face is the overlap between different types of users. So here I've got a Venn diagram of legit users who we know we've got them, and sometimes they fail. Singleton brute forcers, the ones who just, put the pedal to the metal, very easy to detect. And low-rate distributed brute forcers. The things we don't even know. This was another one we went into, not knowing if there were any instances to find. We can tell for a lot of the legitimate users that they're legitimate because, hey, that same user from that same remote host previously successfully authenticated. So it would be sort of perverse if that system got compromised by an attacker who did not manage to get that user's password and is now trying it anyway. That's just not likely. So we can say for some failures, if there's a past history, great. But if the user forgot either their password or username, they're going to fail a number of times. And so will this slow distributed thing. It'll try and fail a number of times. Maybe it'll succeed. Maybe the user succeeds. How do we tell those two apart? Whereas this thing is easy. It's got this high rate unless the singleton is spreading its activity across the entire internet, which some brute forcers do, in which case they'll only touch our site a few times. All right, so that's the lay of the land. Now we go to the ocean. So we had 8 years of data gathered from Lawrence Berkeley National Lab. And you'll hear that name a lot because this has been an invaluable research partnership that the operational security team at Lawrence Berkeley Lab, where I worked for a number of years, collaborates with us on this research. So that's just gold. 8 years of login data. So this is per local server, and there's 2,200 of them. This user tried to authenticate using either public key or password, and they succeeded or failed. 4,000 users, almost 13 million login attempts, of which about 9 million succeeded and about 4 million did not. Now, a bunch of those are login attempts with public key. So if you look at the middle, attempts using passwords, 5.3 million were passwords. So the majority of the attempts were actually public key. And of the passwords, only 1.4 million succeed. That right there tells you how incessant the brute forcing is. So a typical password login attempt at the site is a failure, not a success. And it's a failure because it's one of a zillion done by a brute forcer. And then we have other data here that I'm going to skip for purposes of time and go on to now thinking about this problem. So we understand the problem. We've got some activity that if it were pointwise is detectable, that it's been spread out by the attackers simply to evade detection. And in this case, it's the SSH brute forcing, but it could be other stuff. Anytime you have a threshold-based detector, that has some unit of analysis, like, you know, XYZs per IP address or per domain or whatever, then the attacker has the option to spread out their activity to evade it. So we develop a general framework for detecting this stuff. The framework has two pieces. It has a thing that's going to say the site is under distributed attack. And it's just going to tell us that. By the way, you're under attack. And it's going to do it with high confidence. And we're going to be able to bound statistically the likelihood of it failing just due to benign activity. We're going to be able to pick, actually, gee, I'd only like it to bother me once a year with benign activity. Something like that. And then, once we know, this is one of those times when this distributed stuff's happening, then we're going to figure out who are the perps. Among all the activity going on right now, which ones are coordinating to do this distributed attack? So, this detector is fully principled. It's going to aggregate information about the site into a single parameter that's going to be monitored. And we're going to be able to watch that parameter and compute some statistics on it and know, uh-oh, distributed attack is happening. And we're going to know the region and time it happened. This part, where we're going to figure out who's participating, is not fully principled. We're going to look for commonality among the parties who were active during that time window that the first part got us. And the ones that are common, we're going to infer are coordinating their activity. All right. Where do we get this magic site-wide parameter? The one we're going to use for SSH Bruteforcing is the global failure indicator. We're going to take our logins, batch them up, and the batch size we use here is 100. So we're going to look at every 100 login attempts and just see how many of them failed. That's going to be our global parameter. So we compute it across the entire site. Every 100, how many are failures? How many are failures? How many are failures? Sorry? No, it's, oh, so first, let me add one thing. We removed the singleton brute forcers. They're easy, right? So, because we know, because they're so noisy. So they're all gone. Sorry, thank you, George, for helping me clarify that. So it's not failing all the time, and we'll get the number in a second here. Yeah. Can I hear you? How do we decide what to do with that thing? Oh, yeah, that was the flail around for a month and have a great idea. Yeah, no, that was the hard part. In fact, and I should make clear, by the way, all of the cleverness here was my student, Mobeen Javed. You know, I told her, oh, maybe there's some way to tell they're under attack, and then she figured out this framework, and she figured out this parameter and so forth. So kudos to Mobeen. Whoops, that was not good. What did it just do? Sorry? Yeah. Oh, I think it did a pause. Hold on. You can do it, PowerPoint. I have so much faith in you. I have some faith in you. All right. So that's going to be the parameter. And now, you can think of that as this random variable. How many failures do we get? And as long as distributed attacks are not really common, and that's going to turn out to be the case, then we can forget their effects on this and just treat it as we have a random variable, which is the organic user failure rate. Users fail every 100, assuming it's not an attack, it's a person, and some portion of it fails. And it turns out we can model it, and in fact, we can match it pretty well to a beta binomial. The particulars of the distribution don't matter. The fact that we have an analytic distribution is going to be handy in a minute. So here, this is a plot of, well, what is the distribution of that random variable for each of the years? And you can see that it doesn't change much per year. It moves around a little, not a lot. And so in a given time, the peak is you expect about 7% of those logins are going to fail. Now, again, we've removed the noisy brute forcers. So this is just about all just people. So about 7% fail. Cool. Now, what are we going to do? We're going to use a technique from statistics, change point detection, and the particular one we're going to use is called Q-sum. It's nicely simple. I know it looks a little bit formal here, but let me just walk through it. So basically, we're going to accumulate how many failures have we seen. Every event, we're going to update how many we've seen. So we start with 0. We haven't seen any. And then every batch of 100, we're going to compute max of 0, the previous sum, plus the number we just saw, minus the mean of that process, around 7, minus some adjustment, k. So let me first, if we got rid of everything but the Cn-1 plus x of n, then we've just described a random walk. So we have a random variable, and we're going to just accumulate it. That's a random walk. We subtract off the mean. Now it's a random walk biased around 0. Or not biased, shifted around 0. Okay, so it goes equally up or down. We subtract k means we're actually driving the thing down. So it's not just average around 0, but it's going to tend to skew downward. And then we max it with 0 means we don't actually let it ever go below 0. So this random walk can move up but there's forces pulling it back down. And it will make excursions up. In the absence of any bad guy activity, it's just going to move up, come back down, move up, come back down, move up, come back down. Yes, it's the count of failure. Or it's 0. Yep, it's not negative. So xn is 0 or higher. The mean is around 7, and k is some modest value, which is going to control how quickly we make detection versus false positives. So what's the idea? The idea is if there's a distributed attack, the thing the attacker cannot control is that they're going to elevate the failure rate. They can't do as well as people because people do quite well, only 7% error, and if the attacker can succeed 93% of the time, we are so screwed, right? So then they don't need any sort of broad attack. So they're going to elevate that rate. And as soon as they elevate it above mu plus k, the random walk no longer goes banging into the x-axis. It goes up. So during an attack, so we have some random fluctuation, then the attack happens and the thing just takes off. So we can tell once it goes above some threshold line h, hey, we have an attack. And once it falls back down, we can say, okay, attack's over. That's going to give us the window in time. Now, how do we pick h? Well, you might think, okay, this is a pretty complicated random walk. I mean, geez, it's not the usual one. The usual one, we would know how often would it just benignly go above h. But you can model it as a Markov chain. Okay, depending where you are and what happens, what's the probability. And you know all these probabilities because you know it's a beta binomial. Again, we're talking about the case where there's nothing going on. So we want to know how long will it take to just, due to organic fluctuations in failure rate, go above h. So we can compute what value of h will take how many of these events of 100 logins to have a false positive. And we could set it wherever we like. We can just decide, okay, I'm willing every 10,000 set of logins to have one false positive. So we do that. And now, anytime this detector goes above there, we know with high confidence there's a distributed attack limit. And now we apply, and I'm not going to go into the specifics of this, the analysis of which of the login attempts, which of the remote IPs logging in at that time have commonality to find the participants. And every now and then it's going to not be a true detection, it'll be a false positive. And that's built in. We expect that to happen. All right, how does it work if we run it on 8 years of data? Well, we find 99 attacks. So in that 8 years, there are 99 instances where that detector says you're under attack. 9 of them are false positives. And they're pretty easy to tell once we look at the participants that there's nothing in common with the participants at that time. It's like, this is not an attack. Of the attacks that are attacks, there's 9,300 different hosts around the internet were involved in the 90 attacks. So you can see an average of around 100. And 37 of those we could figure out are classifier or thing that says where the commonality, you find participants by commonality, it made an error. So it's quite accurate. I'm not going to go into those details. This is a nice timeline of those attacking hosts. So we just numbered them starting at 1, all the different remote IP addresses that ever showed up in a distributed SSH attack. And we just plop down a point every time. What we see is that the same hosts come back over months to try yet again to break in. So the attacker is willing to be quite patient here and just throw these attacks at us, months or even years apart. We're able to group the attacks into 35 campaigns. So you might have a distributed attack, and then there's a few minutes of nothing, and then more of it. We grouped all that as a campaign. This is just to talk about it. It's sort of how the site would think about, we had an incident. And then we look at, okay, how detectable were these distributed attacks? And we'd say, if you were looking at an individual host and you had a detector that's looking for too many failures, it would find none of these attacks. So the detector on a host would find none of them because typically it's only seeing 2 login attempts, and that's well within the window of normal user failures. A network detector that could integrate a remote system's activity across all the hosts it tries could find most of them. It could, excuse me. Whoa. Here we go. Sorry. Now, this is not how people write detectors today, so it would need to be a new type, but it's not really hard. However, 4 of them, neither could find. 4 of them are undetectable other than using this. 2 of them succeeded. 1 of them the site knew about, the other one they didn't know about. So that second one was really valuable because the site's then like, oh my goodness. The attacker distributed it. We didn't find it. They do look for singletons. And they got in. And 1 attack targeted specifically usernames at the site. So it was clearly somebody who has already done recon about the institute and is attacking it. Okay, I plan to move on here. If there's questions, I have one more detection problem to talk about. All right, let's talk about social engineering. So the term refers to attacking people rather than systems. One way to think about it, our defense technologies, our technical defenses, gotten better and better over the years, and we've increasingly fixed problems that have lower level semantics associated with them and are moving into vulnerabilities with high level semantics. So what's a low level semantic might be like a buffer overflow. Gee, that's a violation of C's execution model when that happens. And there's a whole bunch of technology to either keep it from happening or detect that it's happened. Higher level would be, for example, cross-site scripting or SQL injection, where there is no violation of the programming model per se. There's a violation of the logic that is supposed to distinguish between code and data. These are hard to detect, and they get harder and harder as the semantic richness grows. Well, what's the highest semantic level? It's what's going on in people's heads. And that is going to be quite hard to detect directly. And this is social engineering. So we would expect to see a rise in social engineering as it gets harder for attackers to go after lower level technical approaches. Now, one form, and the one we're going to focus on, is spearfishing. This is a term. Actually, curious, who's familiar with the term spearfishing? Okay, a few. So let me define it. Phishing is the email that pretends to be from someone, typically email, trying to get you to do something. So like, hey, PayPal, you need to, there's a problem with your account, you need to log into it. Spearfishing is similar, but it is crafted to target the particular victim and has local context to make it believable. So here's an example. This is a medium good one. This one I received. So PGP Signed Message. Whoa, this is official. Turns out that's not going to validate the message. But, you know, looks like it would. Who checks, right? AirBears, that's the wireless network at Berkeley. Your UID, well, some UID, is going to be blocked per the notice associated with this tracking number. That is a correct-looking tracking number. SNS is the security network team at Berkeley. To avoid being blocked, you must go to this link and with your Telnet ID and password. You're going to get suspended if you don't do it damn soon. And you look at the link, and other than the fact that it's HTTP, and it's pathetic, but at that time, that was how Berkeley did this authentication, HTTP, which would redirect to HTTPS. But anyway, off.berkeley.edu. Okay, well, good. All right, that's where it should point to. Well, that's the presentation of the URL. If you actually hover over it, you can see that it goes to, ultimately, off.berkeley.net.ne.net. It does not go to Berkeley. It just looks like it does. If you click on that, you get something that looks exactly like the prompt for username and password used by Telnet authentication. So that is a spearfish. They've gone to the trouble to make it look right. They've got they know that these messages should be PGP signed. They know the lingo, etc. They've done some recon for sure. These are nasty attacks. And in fact, when you look at these, some of these huge, in terms of consequences, compromises and breaches of the last few years, spearfishing is often involved. So, like the some of the disastrous leaks during the presidential election started with spearfishing. Colin Powell was spearfished, and Podesta, I think, was the other guy. All right, now. So we'd like to detect these. And again, it's going to be a needle and an ocean. The ocean is all the email that's not spearfished. We're going to think about this problem along a couple dimensions. You'll see why in a second. Email has a from, and the from is how the user gauges the identity, and therefore the context. The probably number one critical context associated with email is the from. And the from has two parts. It's got the username, Alice Good here, and then their email address, alice@enterprisex.com. Now, the attacker can mess with this in different ways. So we're going to give them some terms, and don't worry too much about these terms, but they can spoof the address. Now, by spoof, I mean the part they're going to keep the same, even though it's bogus, is alice@enterprisex.com. So that's going to be in the email, but it's not going to be where they send it from. And then they'll pick some name, Alice. Doesn't really matter for our purposes. I want to focus on they're spoofing the green part there. Or they might spoof Alice's name and not spoof the email part. And why would they do that? We'll get that in a sec. Or it may just come from somebody we've never heard it from, but it looks pretty impressive. Enterprise X IT staff. But it could be that name is never actually used. It's instead Enterprise X computational services staff, something else, and this email has never been used. Or, and this one is really painful, it really is Alice Good's account. So they've already compromised Alice Good, and they're sending mail from her account. We would like to find these. These are different types. We're going to rule that one out. The reason we're going to rule it out is there's existing technology that an enterprise can use to make sure nobody sends email that claims to be from enterprisex.com from a server that's not authorized to send enterprisex.com email. So that one has an easy fix. We're going to focus on these other three. And the idea is going to be a type of anomaly detection. We're going to look for the confluence of two things. One is we're going to look for something anomalous, something off about the email sender. And there's a URL in the email that gets clicked. So we're going to look for a subset of spearfishing, which is based on URLs taking the user elsewhere where they enter their credentials. By the way, this turns out to be very prevalent. Right? The common thinking is usually it's like an attachment. It's actually not the case as best as I can tell. That happens, but this is very common. Okay, so we're going to try to find those. Here is the ocean. 372 million emails gathered across about 4 years. They come from 3.4 million different usernames. They include 4.8 million different addresses. 2 billion of those emails had a URL in them that got clicked. Now, we don't know that it was that instance of the URL that the user was presented with and clicked. They might have clicked it for some other reason. Don't know. Those emails, there's 200,000 different senders, 30 million clicks. Well, you can read it all. This last part is going to be relevant in terms as follows. When we look for the lateral spearfishing, where Alice's account has been compromised, we're going to leverage the fact that at this enterprise, and many of them, they use corporate Gmail. And so they know what IP address was used to authenticate to Gmail before the email was sent. So it could be it's sent from an anomalous IP address, even though Alice Good is the right name and her email address was right because it was her account. Okay, we want to leverage history that we know, but it's going to be tough, history per sender. We have 4.7 million senders. Nearly 40% of those 4.7 million only ever sent one email. So we have no history for them. We don't know what they normally, what address they, or IP address they normally send from or anything. So we don't know how to gauge how suspicious they are. Why are there so many? Well, spammers tend to generate unique names. And for this project, we're not interested in spammers per se. We only care about spearfish. Spearfish will, some forms of them will be creating names. That's one of the forms I showed. And then there's all these benign senders who just only send once. So we might decide, here I'm walking through a similar argument with the DNS. Okay, let's only deal with users who send at least 100 emails. So we have history. And even for those, we're going to find there's churn. So for example, we might think, all right, we're going to look for a known name, new address. And then we'll say that's anomalous. Unfortunately, this happens quite often. In fact, more than half of our users who send more than 100 emails did it from more than one address. And there's all this automation in there too, that our detector isn't going to know. A human looking at it could say that's automation, but the detector is not going to know. All right, so here is the framework for detection. We have these two conditions. the click was anomalous. There was something unusual about the click on the URL from the email, and the sender was anomalous. I mentioned those before. And we're going to have some features associated with it. So for each click, to decide how anomalous it is, we have two features. The click is in some domain. We look into history in how many prior visits to that domain did anybody at the enterprise make? And we could go back years if we like, but it turns out it's not really going to matter. We could go back a month and that'll be plenty. And the second feature is essentially how long ago was the first visit to that domain. So those are the two. The intuition here is that the spearfish will be taking you to a domain that people don't generally at the site go to. Now, if that's wrong, we're not going to get it. And then we're going to say, is the sender suspicious? And for the hard problem, the one where Alice Good's account has been compromised, we're going to have three features. When that email was sent, there was some authentication by Alice to corporate Gmail. Was it from a different IP address than what she's used before? What city was that in? How many previous emails had been sent by Alice from that city? And the third feature is how many other employees at the lab have authenticated from that city? Those are the three features. So here we're getting at the likelihood that if the attacker has stolen Alice's account, they're not sitting in a city that Alice usually sends email from. So if they're in Berkeley, all right. But if they're anywhere else, it's likely to be anomalous. Now we need to leverage these. We've got these features. In this case, we have 5 dimensions. And we want to figure out, is this given instance of a click from this email, is that pair, the email and the sender, really anomalous? And we might pick some thresholds, like, gee, if only 3 people ever logged in, from that city or whatever, but we don't have a principled way to pick them. We might think we could use ML. All right, let's do supervised learning and learn what's really an anomalous combination of features. And the problem we're going to run into here is the base rate of bad things to give to the ML is incredibly tiny. In particular, we have under 20 known attacks, so we expect there to be very few. And we have a class imbalance of 10 million to 1. So we have way more positive instances than negatives to feed our classifier, and ML does not deal well with this problem, supervised ML. We might try unsupervised ML, where we say, okay, we're just going to cluster and figure out that's a really weird point in that 4 or 5 dimensional space. This is going to have problems. And the problems are going to be threefold. One is clustering generally requires some hyperparameters, things we got to set, like how many clusters. And we don't know how to set them. But let's assume we can deal with that one. 2 other problems is that anomaly detection on clustering, the clusters are going to emphasize being anomalous in just one dimension. I'm going to illustrate this in a sec, or several. And it's going to be agnostic to whether you are anomalous because you're very low or very high. All right, here's an illustration. This is in 2 dimensions. By the way, I've got about 5 more minutes, we're done. So all of these are potential instances of maybe suspicious emails sent by a logged in user. And here we have said, okay, let's figure out that feature. How many logins did the user do in the past from that city? And we've normalized it. And how many employees have previously logged in from that city? And we've normalized it. And so all of the candidates here are spread out there along those dimensions. A classic anomaly detector that's using unsupervised ML is going to be satisfied with something that's anomalous in only one dimension. So it might look at these and say, hey, those are anomalous. They're way over, excuse me, to the right. And they won't care about the direction. They'll say those are anomalous because they're way up there. But for our purposes, that means this is a city the user has used a lot and a lot of other people have used a lot. It's not a worrisome place in the space. In fact, what we want to do is find stuff down here. Stuff that is anomalous in every dimension in the direction that indicates we have a problem. So to find that, we developed a scoring technique for these anomalies to, in however many dimensions, find the ones in that corner. And the way it works is pretty simple. For each point in the space, we just count up how many instances of others activity are as benign as this one in every single dimension. So let me illustrate in 2 dimensions. We're going to have more, in this dimension, you're more benign to the right, and that one, you're more benign to the top. So this point here has a score of 3, because there's 3 above it. This point here has a score of 1, because there's only 1 strictly up and to the right of it. And this one down here, you may have recalled, has 6. So it's the biggie. So if we use that, we can compare a unsupervised technique like kernel density estimation, and this is actual data. So it would find all of these as anomalous because it is happy to find stuff that's very benign, as opposed to DAS, which finds stuff over in the lower left only. All right. That might have been a little more detail than you wanted. Let's get to the results. We'll be done. So we run it, and the nice thing about this detector is we can give it a budget. Here's how much the analyst is willing to be bugged each day. Find them the 10 things they should look at. That's the budget we used. And we know that this is okay because we know from the lab security team that on a typical day, they deal with about 200 to 250 things they got to look at. So another 10 is okay. We look at all those emails. We find 17 spearfishing attacks. We missed 2. How do we know we missed 2? Because they're in the site's incident database. 9 of the 17 we found succeeded in getting the employee to click on the link, but they didn't actually enter their credential. 6 of them that were actual attacks previously known to the lab, and they did steal the credentials. And 2 of them, the lab had not known about. So now, how does the lab find these things? The user reports them, or the attack, or the account is later used. So we're able to find them at the time of click as opposed to user reporting, and we were able to find some that the site never learned about. I'm going to skip over, for reasons of time, the false positives, but the bottom line is these 10 alarms take about, let me get the number roughly right, under a minute a day. And that's because a lot of the detections have these subject lines that are surely not spearfish. So the analyst can just look at it and say, that's not a spearfish. I'm not going to spend any more time on it. All right, so I've walked through these 3. I've been wanting to frame how to think about detection of these needle and haystack problems. And I emphasize that these problems are major pain points used by modern attackers for reasons of stealth. That this problem space is very challenging to apply machine learning to. We lack labels, and we have enormous imbalance between classes even when we have labels. It is really hard due to the diversity that the activity manifests. And the way to go after it is to leverage the underlying semantics of what we're looking at. What is it? Think about what is the actual meaning of the thing we're trying to analyze. In several steps, enormous filtering. We have to identify filtering that we can apply to winnow down the ocean. We have to be content with not solving the entire problem, but some subset that is still interesting and useful. And we need to present, at the end of the day, we have to be content with presenting the analyst with things to look at as opposed to precision detection. And with that, I'm done. Happy to chat further. Thank you. Go ahead. How do you think up the... Yeah, so for that framework where we want this distributed detection, we need to identify a parameter that the attacker cannot manipulate other than away from normal. And so in that space, we have to make that observation. The attacker cannot lower the failure rate. They can only increase it. And that's the art. So we have to think about that constraint. And then we could consider lots of different things. That was the one that clearly has the power. All right. See you.